Hi folks, in this video, we're going to be doing the extended cut, the full explanation of finding the derivative. So in this context, you're in a calculus class, you're given a formula for some function. All right, we're looking at algebraic functions in particular here, so I might have an x cubed and whatever, and let's put a square root in here, okay? We're given some formula for f of x in an algebraic form, and the question is that we're supposed to use the limit definition or use the definition of derivatives or use the instantaneous rate of change to develop a formula for the derivative, the slope function, if you will. There's lots and lots of different words that we would use to describe the derivative of f of x, what we're looking for. This is a formula that represents the slope of that curve at any point, knowing that the curve will have slopes that are different depending on which x value you're looking at. Unless it's a line, then the slope will be constant. We could ask for the instantaneous rate of change or a formula for the instantaneous rate of change. We got these two fun things which represent, these are the limit definitions we're going to look at here in a minute. You might just be simply asked for f prime. That's how we would read that, f prime of a. That's another thing you could be asked for. Or the limit of the slopes of the secant lines, the slope of the tangent line. All of these words and concepts represent this thing we call the derivative. So the derivative, when we say the derivative of a function, we're talking about a function that if I give it an x value, what it's going to give me back is the slope of the curve at that point. And we call this thing a derivative because we can't empirically measure it. If I'm looking at a curve, go here. If I'm looking at this curve here in this top left, and I say, find the slope from here to here, from this point to this point, I can do that. I can connect 2 points and find a slope, just empirically measure it or compute it. If I say find the slope from there to there, I can do that. I can connect those points and I can find a slope. But if I say find the slope exactly at that point, the slope of that tangent line, here I have it illustrated over here too. If I can compute the slope of a secant line by connecting 2 points. Secant line connects 2 points, but I can't compute the slope of a tangent line without knowing something more about the behavior of the function around that point. So I'm basically going to be inferring what the slope is, not computing it directly, but doing some kind of investigation to develop an idea of what that slope should be. I am deriving it. I'm deriving a formula based on f of x. I'm not measuring it. I'm not evaluating it. I'm deriving it. That's why we call it a derivative. So with that in mind, like we can see in the examples on this page, essentially what we want to do, like if you asked me for the slope here at point P on this graph on the left, I would start by taking a point Q that was a little bit further away, and I would find that slope. Then I'm going to move that point Q a little bit closer. Let's move Q down here. I'm going to call this A plus H. Does that make sense? Like if I go from A a little bit further away, I'm just going to add something to A from A to A plus H. So now if I move that A plus H over here and make that distance between them smaller, that line gets closer to being a tangent line and I get closer to having my slope. And the smaller I make that interval, the closer I am to having a slope that represents the tangent slope, or that's equal to the tangent slope. In other words, I want the limit as h goes to 0, h being the distance between the two endpoints of the interval in which I'm finding the secant line. The limit as h goes to 0 of change in y, f of the second x value minus f of the first x value, all over second x value minus first x value. And we're like, oh, a plus h minus a, that's just h. So this formula on this page, this guy right here, he's the one that you're probably going to use 9 times out of 10 if you are asked to do this procedure. It's worth pointing out that in your calculus class, probably in the next week, you're going to get some shortcuts for finding derivatives or stating what a derivative of a function is, just using like tricks and patterns without having to do the brute force calculation and computation of this limit every single time. So in the grand scheme of calculus, you're actually not going to be using this definition a whole lot. But if you are asked to use the limit definition of the derivative, to compute a derivative, to find a derivative, to get a formula for a derivative, 9 times out of 10 in that scenario, you're going to use this one. This h goes to 0 junk, which we typically call the second definition. With that in mind, let's actually do one of these. Let's compute one of these puppies before we look at what we would call the first definition. I'm going to take a quadratic equation here. I'm going to put a number on the front because why not? How about 7? I like the number 7. 7x squared. How about minus 3x? and I like the number 8, plus 8. There's my f of x, and the question would say something like, find a formula for f prime, which means the derivative, using the limit definition of the derivative. That's what the problem looks like. Right, so I'm just going to rewrite what I had on that last slide, which was f of x plus h. We're going to make a's and x's are pretty interchangeable. If you're doing problems at this level, you're probably far enough along that you can just use the variable x if you're asked to find a formula. If you're asked to find f prime at a number, like find f prime of 5, then you could plug 5 in for that a instead of using the variable x. All right, so f of x plus h, that's going to be 7 times x plus h squared minus 3 times x plus h plus 8 minus f of x, being very careful with my parentheses here because I do not want to accidentally only subtract the 7x squared and not the rest of that formula. See, a lot of really smart kids make that very simple error. Don't be that guy. All right, so now we get to do some computation. The next bazillion steps here are going to be straight up algebra, but I will go through them for you. And it's going to get worse before it gets better. You can verify that if I plug in 0 for h in this expression, I'm going to get 0 over 0. And in calculus terms, the conclusion I make is do more work. I cannot come up with a value for that limit without doing more work. I'm going to start by doing some algebra. 7x squared plus 14xh plus 7h squared. You can double check my algebra on that one. Minus 3x minus 3h plus 8 minus 7x squared plus 3x minus 8 all over h. And now we get to cancel some stuff. This should be the step where things start to get a little bit simpler. 7x squared minus 7x squared. Let's see, minus 3x plus 3x. Minus 8 plus 8. I don't see anything else I can cancel with plus or minus. I'm going to write the next step out. You could probably see the next step, but I'm going to write it out here. The remaining terms each have an h in them. So I could say, I could take this 14xh and make it h times 14x. 7h squared is 7h times h minus 3 times 8. And then that's divided by h, which gives me the opportunity to cancel those h's. And now I've got the limit as h goes to 0 of 14x plus 7h minus 3. Now at long last, I can plug in 0 for that h and get 14x minus 3. That is the formula for my derivative. Couple things to point out. If you're taking AP Calculus, be careful to not use that equal sign unless you are sure that things on both sides of that equal sign are actually equal, which in particular in this context means I wrote limit as h goes to 0 every single time until I plugged in 0 for h. Yeah, and also I also didn't do any scratch work somewhere without like writing out the whole expression. It really doesn't take that much pencil lead to graphite, whatever it is, to write out the whole expression every time you write this. I really encourage you to just do it the right way, write equals limit as h goes to 0 of the whole expression while you go through your work. It's just better. So, all right, next up. Next up, the first definition is very similar looking. It says the limit as x goes to a of f of x minus f of a over x minus a. This is exactly the same setup as we had before, only instead of calling this other point a plus h or x plus h, I've just got 2 points x and a, and I'm letting x get close to a, which means as I move this point further along this curve and like closer back to my original point, I get secant lines that are closer to being a tangent line. Exact same idea, but this one's going to feel a little bit different. This would be if I saw a fraction, let's say f of x equals negative 2 over x. If I had an expression with a fraction in it, I would probably choose to use this definition rather than the h goes to 0 definition. So let's go ahead and solve this. If I'm asked to find f prime, the limit as x goes to a. Now I will use the variable a. We're going to see how we have to interpret that at the end of f of x, negative 2 over x, minus f of a, negative 2 over a, all over x minus a. I'm going to deal with this minus sign first before I do any more algebra, being negative 2 over x plus 2 over a over x minus a. You can verify that if I plug in a for x, I will get 0 over 0. That means do more work. So here in fraction land, doing more work is going to mean combining these fractions on the top. I'm going to make a common denominator. So this gives me the limit as x goes to a of negative 2a plus 2x over ax all over x minus a. And now you probably wouldn't think to do this next step unless you were a math teacher. I'm going to factor out a negative 2 out of this top of the numerator. So this gives me negative 2 times a minus x. Cool with that? Over ax. And while I'm at it, dividing by x minus a is like multiplying by 1 over x minus a. Right? I can think of this as like x minus a over 1. I would really, really, really like to cancel this and that, but I can't because they don't have the right sign. So let's say I actually pulled out a positive 2, then this would be negative a and positive x. Limit as x goes to a of 2 times x minus a over ax times 1 over x minus a. Aha! Now I can cancel. And I get the limit as x goes to a of 2 over ax. Now I can plug in the a for x, and I get 2 over a times a, or 2 over a squared. Now I'm going to interpret this as, if I was asked to find a formula for f prime, I'm going to interpret this as being f prime of x equals 2 over x squared, instead of saying 2 over a squared. I could say f prime of a is 2 over a squared, but typically we want that variable to be x. All right, I hope that you found that helpful. Definitely memorize the limit as h goes to 0 definition. I also recommend memorizing the limit as x goes to a definition. Try your hand at some problems, actually computing the limits, and keep me posted in your comments if you have anything to say. Thanks.